All right, so we're talking about our weak acid being titrated by a strong base. So we said that that equivalence point, right, is above a pH of 7. That's because, again, we have this equilibrium up here, right? If we're adding a strong base, we're still going to have this equilibrium where we're going back and forth. So we're going to end up, as we add, right, our OH minus, right, equivalent to our initial concentration of our acid, well, we're going to have extra base in there as well, okay? So that's why our pH at the equivalence point ends up being above 7. Another useful spot here is that half equivalence point. So if we added 20 milliliters of our base, right, at 10 milliliters, we get this half equivalence point. That half equivalence point is actually going to be where we have equal concentrations of our HA, that weak acid, and the conjugate base. Okay? So that is where our HA concentration is equal to that A minus concentration. Okay? And this is really useful because for a long time near here, right, we can add base, but every time we add base, right, we get some going over here, we lose OH minus, and we get this equilibrium occurring, okay? So if we are below that point, right, we have lots of HA. If we are at that point, HA is going to be equal to A minus. And if we are above that point, now A minus starts becoming more and more, right, larger than HA, okay? So we're going to get some practice with this in the lab, okay? So the other piece that we need to talk about, if we have a base that we start with, right, maybe it's a weak base, and we titrate it with a strong acid, that would be where we start up here, and then we drop down, and then we go here. Again, we've got that same equivalence point, right, where the amount of acid that we've added, the number of moles of acid that we've added, is equal to our initial base numbers. Again, we've got this equilibrium that occurs. So our equivalence point, right, is going to be below 7, okay? It's going to be below 7 there, right? Again, we've got this near this, with that buffer zone. We're going to talk about buffers in a second here, right? That buffer zone where we have our half equivalence point, where the base is equal to our conjugate acid, but then we have, right, our regions where we have more of that base or more of the conjugate acid, okay? If we have a polyprotic acid, right, let's talk about polyprotic. We're going to have multiple humps, okay? So if we have a polyprotic, right, maybe it starts out real low, we get a buffer zone, and then it's going to jump up, and then we'll get another buffer zone, and then it's going to jump up again, okay? So if we get that polyprotic, right, we're going to see that we could lose multiple protons there, okay? So that's what we're going to end up seeing, right? We should hopefully see this in the lab. Okay, so let's go ahead. We're going to go on to the next page. All right, so buffers, okay? So buffers, let's talk about what a buffer is. We just said, right, that if we have a titration, right, we've got this point where for a long time we're adding our titrant, right? We're adding that weak base, a strong base, our weak acid, we're sitting there for a while, and then finally it starts going up, okay? This is our buffer zone, okay? The buffer zone is when a solution that contains large amounts of an acid and base, right, of that conjugate pair, right? So conjugate pair. Okay, so if we have a buffer, right, we've got a large amount of both our acid and conjugate base, or the base and the conjugate acid. Okay, so we've got this mixture of both of those, right? So if we have a base that or an acid that we've put in there, right, we would have pH and pKa. Okay, so if we have the pH, right, and our pH is less than the pKa, right, then the acid is going to be in higher concentrations, right? That's where I said we're over here in this portion, right? Our pH is below that pKa, okay? If we have a pH that is greater than the pKa, then we're over on this side. Now our base form, right, the conjugate base, would be in higher concentration, okay? So this all comes out of the Henderson-Hasselbalch equation, okay? So the Henderson-Hasselbalch equation, this is on our equation sheet. That is pH is equal to pKa plus the log of A minus over HA. Okay, so this comes out of, all this is, right, this, we can derive this if you would like, but it comes out of the, oh, I wanted it down there. This comes out of our equilibrium expression, right? That's all it is we're just taking that equilibrium expression and we're just rearranging it, solving for pH rather than pKa, doing rules with logs, okay? So that's our Henderson-Hasselbalch equation, right? And now, so if we have this, right, and we have A minus in a one-to-one relationship to HA, right? HA equals A minus, right? Log of that, right, some number divided by the same number would be 1. Log of 1 is going to be equal to, right, log of 1 would be equal to 0. So pH is equal to that pKa. Where is that on the graph? That's right here in that center of that buffer zone. Okay? Okay. So if we're near that pKa then, right, we can actually use this equation to calculate how much our pH changes, what our concentrations are, and it's really that it's not going to significantly change because of the addition of acids or bases, okay? We oftentimes in the lab, we use indicators to help us with these titrations, okay? Okay, so let's do some of that practice, right? Let's do some of that practice. A buffer is prepared by mixing 500 milliliters of 1.250 molar ammonia and 25 grams of ammonium chloride. We have NH4Ka is 5.6 times 10 to the minus 10th. So if we see here, right, we've got 500 milliliters, we've got 1.25 molar ammonia. So let's calculate, right, our number of moles of NH3, right? Ammonia would be NH3, so 1.250 moles per liter times 0.5 liters. That's going to equal, make sure I get all of this right, I don't want to screw it up, equals 0.625 moles of NH3. Okay, so now then we added 25 grams of ammonium chloride. Well, 25 grams NH4Cl, we can of course convert that to moles. 1 mole is 53.55 grams. So that's going to be 0.467 moles of NH4. Okay, so now we have those two, right? We should be able to calculate the pH, right? So pH equals pKa, we have our Ka, so negative log of 5.6 times 10 to the minus 10th plus log of, we're going to do concentrations, but the concentration, right, the liters cancels out, so we're going to get we're going to have basically just moles. So we're going to do moles of A minus, that would be NH3. So oh, whoops, I screwed that up there. But 0.625 over 0.467. That should equal 9.38. Let me check my numbers.